most people will say infinite series. The gauntlet. So we're that much closer. It's like the white slide at Waterworld. The big white slide at Waterworld. It's fun but scary. Okay, so let's see, I think we finished that last example. All right. All right, so we're going to finish up. We have a couple more slides in 8.5 with the partial fraction decomposition. And this section, for most people, once you put enough time in to sort of get the structure of partial fraction decomp, is pretty straightforward. The next section's a little more abstract. This section, if you put in enough time, it'll feel like, okay, I've got a procedure. Figure out the form for your PFD, solve using either traditional method if it's a non-linear. So if it's an irreducible quadratic, the traditional method usually works better. And if it's linear factors, we can use the convenient value method if it's linear factors. So let's do an example here. So it's a cooked up application. We're just trying to find the area of this region here. So I drew a graph of the region right there. We'll use a vertical integration element, and we'll integrate from 0 to 1. The main part of the problem is that the fraction up here has a factored denominator. So factored denominator is where we sort of think PFD, because we can break it apart. And the PFD concept is that we break it apart into two fractions that have those denominators. Right? That's the whole idea of PFD, is that if we can factor the denominator, then we can bust it apart. So let's go ahead and try to break this thing apart. So it's already factored for us. So remember that if you see a denominator that's not factored, it would have to be factored before you could even consider PFD. So you need to have it factored first. And the next step, once it's factored, is to identify the nature of those factors. And when we look at this factor right here, is that one linear or quadratic? That's going to be linear because the power in x is 1. And this one is an irreducible quadratic. So remember that irreducible means we can't factor it unless we use imaginary numbers, and we do not want to use imaginary numbers here. So irreducible quadratic. And the way we set up our PFD is that we are going to put a constant over any linear factor. And we're going to put a line or a linear expression over any quadratic factor. So those are our two basic rules for PFD. Linear denominator, constant numerator. Quadratic denominator, linear numerator. And now just for the sake of it, if this happened to be squared on the irreducible quadratic, we would have to have another factor, another fraction I should say, dx plus e over x squared plus 1 squared. If there was a square there, you have to have a fraction for every power of the factor in the denominator. You have to have a partial fraction for every power. But we don't have that, but if it was, we would do that. Similarly, if there was a 2 here, on the outside of that linear factor, we'd have another, something over x plus 1 quantity squared. So we have to have a fraction for every power. Okay, so this has a linear and an irreducible quadratic. We're thinking we'll probably go with the traditional method then, because there's not a convenient value for x squared plus 1. You could force the convenient value method to work, but usually if you have an irreducible quadratic, it's just easier to do the traditional method. So we're going to take that yellow box right there, we're going to multiply all fractions in this equation by that yellow box. So on the left, when we multiply by that, it just clears out the fraction. On the right, we are multiplying it by this fraction and by that fraction. And we're distributing. we're multiplying both sides by that denominator. So on the right-hand side, when you multiply by this yellow box, the x plus 1s cancel with this first fraction. So we're left with a multiplied by the quantity x squared plus 1. And when we take that yellow box and multiply it by the second fraction, the x squared plus 1s are going to cancel. And we're left with x plus 1 multiplied by bx plus c. Any issues with that? So all we're doing is multiplying by the denominator on the left to clear the fraction. That is our PFD equation. This is where we can decide to go traditional or go convenient value. Again, there's only one convenient value, -1, so let's just go traditional. We could do a hybrid approach too. You could use a convenient value method to try to solve for one of the letters and then jump into traditional. Does not matter. But we'll just go traditional method the whole way. Every day, one time it does that? What is that all about? So we're just going to multiply this all out. So there is our PFD equation. That equation is what's going to build our system. So now let's build our system. And maybe, it doesn't really matter, but on the left-hand side, you have a polynomial. Maybe it's better for you to write it in descending order. It doesn't matter, though. We just need to identify the coefficients of the square term, the linear term, and the constant. So let's go with the square term first. So there is the coefficient for the square term right there. Let me just highlight the whole thing. And then on the right-hand side, there are the square terms. So the coefficient of the square term on the left is -1. That means the square coefficient on the right-hand side must also be -1. So we have -1 equals, let's see, the coefficients on the right would be a plus b. So that's the coefficient of x squared, left and right. And then we're going to go to coefficient of x. So we're going to look at the terms that have just a single x. And on the left, the coefficient is +1. On the right, looks like b plus c. Question?
Like, what are you doing to get that?
The coefficient of x here is 1. The coefficient of x here is b. The coefficient of x here is c. So those are added together. So we're looking at the letters. We're looking at the coefficients in front of x and matching them. We're looking at the coefficients in front of x squared and matching them. And then the last thing is to look at the constant. And what is the constant on the left? 0. And how about the constant on the right? A plus c. It's the a's, b's, and c's that have no x in them. So it's a plus c right here. Let's use that. So there's constant there and constant there. Does that make sense? So the constants are the terms with no x's. And those all have to be equal, just like the number in front of the x's have to match and the numbers in front of the x squares have to match. So all those have to line up. So there is our system. And now we're back to algebra. We just have to solve that system. 3 equations, 3 unknowns. You can use substitution, you could use elimination, whatever feels best. Does not matter. So, I don't know. This equation has a 0 in it, so it's going to be really easy to do substitution here. You can solve for a and get a to be -c and then plug it in up here. So what we have to do is have 2 equations that have the exact same variables. Right now, we don't have 2 equations that match. Everyone agree? And we have an a and a b and a c, and an a and a c. So we don't have 2 that match. So what we're going to do here, substitution seems like a pretty reasonable way to go. So we get that. And then we're going to plug it in up here. We're going to go say, OK, well, let's replace that a with -c. So this is going to create the following system. Now we're going to have 2 equations and 2 unknowns. When we plug in the -c there, we have -1 equals -c plus b. So we took this equation and combined it with the first equation. Now we haven't used the second equation, so we need to use this second equation. So these are the two that we have left. We combined equation 3 and equation 1. Now equation 3 and equation 1 combined have the same two letters as equation 2, so now we can combine those two. And that's not in order because we replaced the a with negative c, but obviously we can reverse the order. Now the simplest way to solve this is just to add. If we add these two equations together, negative 1 plus 1 is 0. Negative c plus c, 0. And b plus b is 2b. So we added those two equations together. Add the c's, add the b's, add the constants. That tells us b is 0. So now we have one of our three constants solved for. What does that mean c has to be? 1. We plug it back into either equation. Does not matter. Either equation here. So this is going to tell us that c is 1. So now we have 2. And then to get the other letter is a. So we can come right here. A is equal to minus c. So that tells us that a is going to be negative 1. So now we have all three of our coefficients. And now we can take our original integral. So we're going to have x minus x squared. Okay, so we have the integral of x minus x squared over x plus, was it x plus? I can't even remember. X plus 1 and x squared plus 1. So we have that. So that's our original integral. And now we can rewrite that with these coefficients. So a over x plus 1. So negative 1 over x plus 1. And then we had bx plus c. So b is 0, so bx, that's 0x plus c. That gives us plus 1 over x squared plus 1. And this should be a definite integral, because we're finding area between 0 and 1. If we look at our graph, we can see that our vertical rectangles are going from 0 to 1. So we'll put limits of integration on here, 0 to 1. And there we have it. So any step in this setup that you aren't sure about?
I didn't hear where you got the limits.
The limits of integration are coming from our physical region. So we're trying to find the area of this gray shaded region here. So x is 0 on the left and 1 on the right. And we have vertical rectangles, so we're looking at x limits of integration. Yeah?
So the a over x plus 1 plus the bx plus c,
Mm-hmm.
is that just like a thing we have to memorize?
Yes. Anytime we have a linear factor in the denominator, we need to know that we put a constant in the numerator. And anytime we have a quadratic factor, we have to put a line in the numerator, a linear expression. Yeah, so that's what we need to know about PFD. So the power in the numerator is always 1 less.
If you have a linear term squared or to some n power, you just, it's the first and then over a constant and then it plus
Yes.
the constant over the squared version and
Yep.
then so on and so on.
I'll write one down because I know exactly, I have a good example I'll show you in 1 second.
Okay, and then the same thing if it's a quadratic, it's just bx plus c over 1, 2, then 3.
That's right.
Okay,
Yeah.
sorry.
We'll do a general one where we don't solve it, but we'll just write it out to make sure that we see. Now both these are immediately integrable, correct? Instant antiderivatives. What's the first one? Natural log. So minus natural log absolute x plus 1. And the second one? Arctan. Good. So we have instant antiderivatives for both of those. We don't have to do any manipulation. And notice here, when we plug in 0, 0 is going to give us a natural log of 1, which is 0, and inverse tangent of 0 is also 0. Natural log of 1 is 0, arctan of 0 is 0. Arctan of 0 is 0. You can say it conceptually, inverse tangent of 0 is the angle on the right with a tangent value of 0. The angle on the right with a tangent value of 0 is 0 radians. Or you can think of the picture. And the picture of arctan, we're going to start looking at it more and more as we get into the subsequent sections here. The picture of arctangent is interesting because it has two horizontal asymptotes. You don't see a lot of functions with two horizontal asymptotes. So it is going to become, that's part of the reason it's going to become super useful later on is because the limit as x goes to infinity and as x goes to negative infinity both exist. So arctan of 0 is 0. It goes right through the origin. Okay, so all we have to really concern ourselves with is that upper limit of integration. So we're going to have negative ln of 2 plus arctangent of 1. And what is arctangent of 1? Pi over 4?
Yeah.
Pi over 4. So we're saying to ourselves, what's the angle on the right with a tangent value of 1? And that's right at 45 degrees, pi over 4 radians. So this will be our final answer. That is the area of the region, the shaded region. All right. So let's get to Oliver's question about repeated roots. Repeated factors, I should say. In college algebra, you talked about repeated roots. You called them multiplicity. If you're looking at a 0, if there was a power more than 1, you called it a multiplicity 2 or 3. Here we're talking about the factors more than the roots. So we call them repeated factors. So if we had something like this, so let's just write down the PFD for that. So you should see two factors. The factors that you should be seeing are this one and this one. Those are the factors. The factor on the left is not x cubed. The factor is x, but it's repeated 3 times. And if you are thinking to yourself, well, isn't it usually like x plus 1 or x minus 2? Yes. You could, if you want to, you can think of it in your mind as this. It's x minus 0 quantity cubed. Right? So the 0, we don't write it down, but the 0 is the 0 of this factor. So this is a repeated factor, a repeated linear factor. And so here is what the PFD will look like. So we need to have a constant divided by each power of that linear factor. So there we have it. That is for the x cubed. We have to have a partial fraction for each power of that repeated root, that repeated factor. And then we go over to the x squared plus 1 and we say, okay, that's an irreducible quadratic. So we have a quadratic factor. So the numerator needs to be linear. So we're going to have a dx plus e over x squared plus 1. But then that factor is also repeated, so we need another fraction to take care of the second power. And what will that numerator be? fx plus g. If you need to write down the alphabet, that's fine. If you can't. So that's the setup. Now, how many equations will we need to solve this? How many equations would we need? 7. Right? In college algebra, you learn 2 equations for 2 unknowns, 3 equations for 3 unknowns, 4 equations for 4 unknowns. You would need 7 equations here. So we are not going to solve this. We are not going to solve 7 equations and 7 unknowns. That would be very, very hard. When you get into a class called linear algebra, you can solve systems that have 7 equations and 7 unknowns very easily with something called a matrix. A matrix is like synthetic division on steroids for systems of equations. You erase all the letters and you just have numbers in an array. You can solve it very easily with matrices, but we're not going there. Okay, so that's the basic setup. This is what you need to know about PFD. This is everything, right? We have a linear that's repeated, so you have to have constant, 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 and then we have a quadratic that's repeated, so we have to have linear and linear on the tops. That's the part we have to memorize. All right. Final. Oh, I know you're excited when you see this word. Right there, that word is just very, very exciting. Volume. It's like stepping into 3 dimensions. It's always nice to get off the paper. Okay, so we have our region here. The graph is shown. We want to find the volume of this solid that's going to be rotated around the x-axis. It makes the most sense to use a disk. When we look at this, if it's rotating around the x-axis and our function is a function of x, we really want to preserve the function of x thing. That we don't want to solve that for x. We wouldn't want a horizontal horizontal element. That would be really bad because right here, drawing horizontals here would be a terrible idea. Because here it hits the curve here and then it stops. That would be very difficult. We'd have to break it into 2 regions because there's not a common left and a common right. So definitely vertical is the way to go. And that's going to give us a disk. So that's going to rotate around and give us a disk. The radius of the disk is right there. It's the function value. And so the area of a disk is pi r squared. And the radius is the function. So that distance from the axis of rotation up to the curve, that's what the function measures. So we're going to take our function and square it. So the area of our disk is that. That is the area of our disk. Any questions on that? Area of the disk? Everyone see the disk? As this rotates, that element rotates around, we're getting a disk of radius r. Yeah? Yep, let's use symmetry. What are you thinking? So if we go 0 to 1 and double it?
Yeah.
Totally agree. So we'll go 0 to 1 and double it. So this is a symmetry 2. There is just as much volume to the left as there is to the right when you rotate those 2 shapes. So we can just double it. Always having a limit of integration that's 0 is helpful. Okay, so what we know is that if you integrate area, you get volume. Integrate area, you get volume. So we already found our area. We just have to integrate that. So we're going to integrate this area, and that will give us volume. Square. Now, that thing is factorable, but what we usually like to do when we're factoring is have the leading coefficient of the square term be positive. It's a lot easier to factor in general. Now you could 2 minus x and 2 plus x, yeah, okay, you could do that pretty easily. But with the whole PFD thing, it's usually just a little easier if you write it with descending order. So I'm going to factor out a minus sign just so it's written in descending order. And we can factor out the pi as well, right? So the pi can come out. We'll still go 0 to 1, and we're going to have dx over x squared minus 4. So as soon as we recognize that the denominator is factorable, that sort of makes us think PFD. Now on the exam, I will tell you, I'm not going to try to be sneaky. I'll just tell you to use PFD. But in general, that's your rule of thumb. If it can factor, then PFD is a good way to go. So we're going to take the inside of this integral and let's rewrite it using partial fraction decomp. So we're going to take the inside of the integral. And we have two linear factors. So that's going to be our decomp. And we'll go with the same procedure we've been going. Multiply both sides by the left denominator. And if you multiply both sides by the left denominator, you get a cancellation on the right with each fraction. Linear factors, usually it's a heck of a lot quicker to use convenient value method. So convenient value method, what are the two convenient values for this case? Minus 2 and 2. Right? They're the zeros of those factors. So let's go ahead and use those convenient values. So convenient values, we have x equals -2 and we have x equals 2. And so the whole idea is that this equation is true for every single x. It's an identity. So you can pick whatever x's you want. If it's true for all x's, then it's true for a -2. And if you plug in -2, you get that equation. And if you plug in +2, you get this equation. So the convenient value method is a great way to go if you have just linears. It will always, one of the few times in math we can say, it will always be faster using convenient value if you have distinct linears. It's always going to be faster. All right, so that allows us to rewrite our integrand. We still are going to have limits 0 to 1. We're going to rewrite our integrand as 1/4 over x minus 2. And then we're going to have minus 1/4 over x plus 2. Should we factor the 1/4 out? Seems like a good strategy, get it out of the way. So that 1/4 is going to come out in front and leave us with -pi divided by 2. 1/4 of 2 is 1/2. And how about, what's the integral of 1 over x minus 2? It's going to be a natural log. And similar for the second one, right? So we're going to get natural log absolute value x minus 2 minus natural log absolute value x plus 2, 0 to 1. So plugging in 1 is going to give natural log of -1 in absolute value. So let's write it out. Minus natural log of 3. Then we're going to subtract off the antiderivative at 0. So we're going to have minus natural log of -2 in absolute value minus minus is plus, natural log of absolute value of 2. So we end up with that. These two cancel. Absolute value of negative 2 is 2, so we have minus a natural log of 2 plus a natural log of 2, so that cancels. How about natural log of negative 1? 0. So that's going to equal 0. So the only thing left is minus natural log of 3. So we have minus pi over 2 times negative natural log of 3. And the minuses will cancel, so we get pi over 2 times natural log of 3. So that's going to be the volume. So we got
I think you did it from 0 to 1, and it shows on here negative 1 to 1.
right, we doubled it.
Oh.
So the negative 1 to 1 is the whole thing. And so if we go 0 to 1 and double it, that'll have the same effect as going negative 1 to 1. Yeah. That makes sense?
And then, I had
Yeah,
one more.
sure.
Where'd you pull out the negative from? For
This negative right here?
yes.
So I factored it out of the denominator.
Oh, gotcha. Okay, I
So
see.
that can come out to the front
Okay.
just to make that descending order. You don't have to do it, but generally descending order for polynomials is usually easier to manage when all is said and done. But if you wanted to do 2 minus x and 2 plus x, that would also work. You just have you'd have an a over 2 minus x and a b over 2 plus x. It's just a little. It's not the way we usually do it, so. Any other pieces of that you want to look at? Make sense? PFD, pretty darn fun. Yeah? It's going to be more fun than what we're about to do. 'Cause now we're going to have the rubber band imagination happening. Get ready for the rubber band imagination. Here we go. So improper integration is the perfect segue into what we are going to do in chapters 10 and 11. So chapters 10 and 11 are the infinite series. And before we even talk about infinite series, before we even talk about these improper integrals, I want to ask you a basic question. Simple question. Simple to state. Can you add an infinite number of positive values and get a finite result? Can you add an infinite number of positive values and get a finite result?
Yes.
You would say yes. Give me an example.
+1 and -1.
Positive values. Positive values.
I don't know that.
Jesus?
You do a bunch of decimals.
Mm-hmm. So our immediate instinct is that something's wrong. If you're adding an infinite number of positive values, how in the world could that be finite? Because our instinct is to start thinking about adding integers and things. But if we look at something like 0.3 plus 0.03 plus 0.003, this is an infinite sum of finite values that will give us a finite result. An infinite sum of positive values that gives us a finite result. Everyone agree? Right? So that is at the heart of improper integration and infinite series. That is the key, is that you have to be thinking that it is totally fine to add an infinite number of positive values and get a finite result. And when we get to chapter 10 and 11, the question is going to be, we're going to see that there are some thresholds that obviously this one you can add together and get a finite result. But there are going to be some that are not so obvious. Like clearly, if you want to get a finite result, you need to be adding terms that are getting smaller and smaller and smaller, right? They have to be going to 0. If they're not going to 0, then it's going to get bigger. It's not going to be finite, right? If these terms aren't going to 0, there's no way you could end up with a finite result. You can imagine blowing up a balloon. If you're now putting in just a tiny, tiny, tiny bit at the end, it's going to explode. Right, so you've got to be adding numbers that are getting super close to 0. Here's another example. This is an example where you are, in fact, adding numbers that are getting closer and closer and closer to 0, but this will go to positive infinity. So it's not enough to say that each term is smaller than the prior term. That's not going to be enough. So that's what chapter 10 and 11 are all about, figuring out when an infinite series is going to have an infinite result and when an infinite series is going to have a finite result. And so that's kind of in the background of what we're doing. So just have that in the background. And the reason that that's a good backdrop to what we're about to do is that with improper integration, we are going to try to find the area of an unbounded region. Some people will call it an infinite region. That's not really the best way to use the word infinite. So this region goes on forever and ever. So it's unbounded. It doesn't have bounds. Like a definite integral, like we just did a minute ago, bounds, -1 to 1, 0 to 1, whatever they happen to be. So that's a definite integral. You have boundaries on the left and the right. So for an improper integral, you're going to have a tail. And we're going to see that we can have tails to the left or a tail to the right. Tail to the right, tail to the left. Or you could have a vertical tail. We'll get to vertical tails in a minute. But it's possible to have your region go on forever up or down. So the first introduction to this, we're going to look at tails that are horizontal, either off to the right or off to the left. And so this is why we need to understand that. Because area is really an infinite sum. Right? You take the limit of a Riemann sum. A Riemann sum is an infinite sum. The rectangles, you're letting that n go to infinity, so you're adding up an infinite number of rectangular areas. And you can add up an infinite number of rectangular areas and get a finite result sometimes, but not always. So you're imagining here all these rectangles. So we're imagining all these rectangles here. And if the area pattern is something like that, then you can have an unbounded area. So unbounded means it goes on forever. You can't put a circle around it. It just keeps on going. So you can have an unbounded region that has finite area. Totally possible. You think that in your head, right? If this is the area of rectangle 1, and that's the area of rectangle 2, and that's the area of rectangle 3, etc., you can have an unbounded region with finite area. All right? Slightly counterintuitive, but it's very possible. Here is what our strategy is going to be. Our strategy for an improper integral is that we're going to say, hey, we know how to do a definite integral, so let's just create a definite integral from a to b, and then take the limit. And in your mind, you should be thinking, oh yeah, that's like the limit of a Riemann sum. It's the same idea. If we can find a function that measures the area from a to b, then we can take the limit of the function as x goes to infinity. All right, that's going to be our strategy. Is that, okay, well, let's just look at this finite part, and let's let b creep out further and further and further. Let's take the limit as b goes to infinity. And that will be our strategy. So when we look right here, this is step 1. Step 1, when we have an improper integral, is to turn it into a limit of a definite integral. So every single time we have an improper integral, limit of a definite integral. That's our strategy. So we are going to take the limit of a definite integral. So that's the strategy. Now, when you have a horizontal tail, it's so obvious because you see right in the limit of integration an infinity or a minus infinity. Right? You can't miss it. It's right there. So that tells us. We are going to see that when we have vertical tails, things are a little more obscured. When we have a horizontal tail, it just jumps out at us. We see, oh wait, that's not a definite integral. A definite integral has integers or real values here, right? Not infinity and not negative infinity. This is not definite. So that'll be our strategy. If the tail is to the left, the only difference is that we are going to take the limit as a goes to negative infinity here. So they're going to call our interval AB. If the tail is to the right, they're going to let b go to infinity. If the tail is to the left, they'll let a go to negative infinity. So that's our strategy. One side note here, if we happen to have a curve like this where it's unbounded to the right and unbounded to the left, you cannot just integrate from negative a to positive a and take the limit. That will not work. You'll have all sorts of weird things that happen. We'll talk about some of those later. What you have to do is bust it apart. You have to break it, and it does not matter where you break it. You can break it at 0, you can break it at 5, you can break it at negative 5. It does not matter. But you're going to treat this one as a right tail, and you're going to treat this one as a left tail, and then add them together. So you have to turn it into two separate integrals. So you turn it into a left tail and a right tail. So this one has a right tail, and this one is the left tail. So you have to do them separately and treat it like you have two separate improper integrals. And if both of those are finite, then the total is finite. If one of them is not finite, then the total is not finite. Right? Finite plus infinite is infinite. So both of these areas individually would have to be finite for the total area to be finite. Okay, so these horizontally unbounded regions, here one is. So again, this is an example where we're going to look at a right tail, and they're just kind of indicating here, hey, look at the b. If we let the b slowly go further and further out, in other words, take the limit, let's see what happens. So here's where we start. We're going to start with the limit. No, not limit yet. First, the integral. So the integral from 0 to infinity of 1 divided by x squared dx. So that is our improper integral. Say again?
Is it 1?
Oh, 1. I'm sorry, 1. 0 is a bad lower limit because it's undefined at 0. We would have a vertical unbounded tail if we started at 0, which we will do soon, but not yet. Thank you. So 1 to infinity. So first step always with an improper integral is turn it into the limit of a definite integral. So this is going to be the limit as b goes to infinity. And we're going to make this a definite integral. We're going to go from 1 to b, and we're going to rewrite this as x to the negative 2, since that's how we integrate. Powers of x in the denominator. So that is the limit of a definite integral. Analogous to what you did in Calc 1, where you did the limit of a Riemann sum. Analogous. An integral is a sum. That's why its symbol is an S for sum. So then we just let the limit sit out here in front. If you don't have to constantly keep rewriting the b goes to infinity if you don't want. It gets a little old if you have to write it 10 times. At least write the word limit. So now we integrate. So this is x to the minus 1 divided by minus 1 from 1 to b. Power rule, add 1 to the exponent, divide by the new exponent. And this will become the limit. Let's just rewrite it. I find that it's sometimes easier to analyze limits when you don't have negative exponents. Some folks are fine with negative exponents, but in general, it's usually easier to look at a limit when you don't have any negative exponents. So let's just write it like that. This is going to be the limit of negative 1 over b minus a minus is plus 1 as b goes to infinity. And that limit is it's going to be 1 in total. The 1 over b part, that of course goes to 0. If you have a constant in the numerator and a denominator that's growing without bound, it's growing bigger and bigger and bigger, that fraction's got to go to 0. So in Calc 1, you had 2 basic limits. So here were your 2 Calc 1 basic limits. Your basic limits were the limit as x goes to infinity of x, that's infinity, and the limit of 1 over x as x goes to infinity, that's 0. Right? Those are your 2 basic ideas. If the x is in the denominator and the numerator is a constant, it's going to go to 0. So this tells us that this area is finite. That area is finite. So under x squared, from 1 to infinity, that's the area in integer. You would never, even if someone told you that that area was finite, you would never guess that it was integer valued. You'd say, it's probably some fraction of pi or something weird. So that area, that unbounded region, has area 1. Okay, so one of the themes that we're seeing is that in order to have finite area, clearly the curve has to approach the x-axis. And it's got to approach the x-axis fast enough that we're getting, we can think about the rectangles shrinking quickly enough in area. So it's got to be approaching the x-axis fairly fast. And that's what all of chapter 10 and 11 is about. Well, what does it mean to be fairly fast? What does it mean to be fast enough? That's what we're going to figure out in 10 and 11 mostly. And here too. So, any questions on any of the math there? So the only new thing is this step. That's the only new thing. Is that if you have an improper integral, you turn it into the limit of a definite integral. You already know how to do definite integrals. Find the antiderivative, plug in the limits, take the difference. You already know that. And you know how to take a limit. All right, so there was nothing at the bottom of that, right? So here we go, another one, another right tail. Graphing in Desmos, you can sometimes get a hunch. Just looking at that graph, it certainly looks like it goes to the x-axis fast, right? And if you look at the function is an exponential decay. 2 to the negative x, that's exponential decay. And we know that when you hear the word exponential growth or exponential decay, you think fast, right? It's either growing fast or decaying fast. And so it's reasonable to think that this probably is going to converge. We'll use the word converge if the area is finite. All right, so again, very first step, you immediately write limit, always. So the limit as b goes to infinity. So you recognize that it's improper because you have an infinity staring at you. Then we turn it into a definite integral. So we're going to go limit from 1 to b of this function dx. And then we integrate our exponential function here with base 2. So limit, the integral of an exponential is itself, always, any exponential, regardless of the base. First thing is the integral of it will be itself. And then we have to do RCR, because that exponent is not just an x. That x, it's a negative x. So we have to take the derivative of that and divide by -1. So that's RCR. Right there, RCR. Reverse chain rule, because of this negative right there. And you all know that that's not a natural exponential. If it was an e to the negative x, we'd be done. But when it's not a natural exponential, when it's not an e, we have to do a little modification. Anyone remember what that modification is? So we have to do something with natural log of the base. Natural log of e is 1. So natural log of 2 is not 1, so do we multiply by it, divide by it? You remember? Divide is going to be the right answer. If you just sort of think about reverse chain rule, right? With reverse chain rule, we divide by the derivative of the exponent. So with integration, there's always this extra division. With chain rule, there's extra multiplication. With derivatives, there's extra multiplication. With integration, there's extra division. Let's just point out, let's go back to Calc 1 for a minute. If you wanted to find the derivative of 2 to the x, do you remember how you found the derivative of that? To prove what the derivative is, you did something called logarithmic differentiation. So you took the natural log of both sides, and when you take the natural log of the right-hand side, that x can come down in front, laws of logarithms, and now you can differentiate both sides using implicit differentiation. So at this stage, now we're going to take the derivative of both sides. So we're going to take the derivative of the left side and the derivative of the right side. The derivative of the left side, it's a log, so it's 1 over the inside multiplied by the derivative of the inside. Well, the derivative of y is called y prime. And what is the derivative on the right-hand side? Derivative is
L2.
natural log of 2. Right? It's just a linear function of x. It's a constant times x. If somebody said, what's the derivative of 4x? You'd say 4. Derivative of natural log of 2 times x? Natural log of 2. Right? That's just a linear function of x. So the derivative is the coefficient. And then we isolate the y prime, since that's what we're trying to find. So y prime is equal to y times natural log of 2. Well, what's y? 2 to the x. So that's how we show that the derivative of an exponential with base other than e has this extra multiplication when you're differentiating. And you can do the same type of thing with integration, but you're going to get that. You're going to divide by it. So we're going to divide by natural log of 2. So if you have a non-e, you have to make that little correction. With integration, divide, derivatives, multiply. Okay, so you remember that? I think you should have been taught that. Were you? Yes. Admit it. It's okay to have forgotten it, because we don't use it a ton. All right. So now let's go ahead, and another rule of thumb that you don't have to do this, but a lot of times when you're taking a limit, it's easier to get rid of all the constants so that you just have the variable part that you're analyzing. Oh, and I did something bad. Here's what I did that was, I need this still, right? We're going from 1 to b. I forgot that part. It's a definite integral. So we still need our limits of integration. So we need the 1 to b. So, and what I was just saying is that it's very easy to get tangled up when there's a lot of constants in here. Again, you don't have to, it doesn't matter. But I tend to factor out the constants to the front before I evaluate the limit. So I'm going to pull this negative natural log of 2 out to the front. And then we're going to have 2 to the negative b, plugging in the upper limit of integration, minus 2 to the negative 1. Everybody agree with that? So the only part in there that's variable is the 2 to the negative x. So we plug in the upper limit, get 2 to the negative b, plug in the lower limit, get 2 to the negative 1. And before we evaluate the limit, like I did on the last one, I think it makes it a little easier if you get rid of negative exponents. Negative exponents tend to be bugaboos. Tend to cause a little bit of grief. So if we get rid of the negative exponents, what is the limit of that first fraction as b goes to infinity? 0. Because 2 to the b is going to infinity in the denominator. If the denominator is growing without bound and the numerator is a constant, that means the fraction values are shrinking to 0. So that is going to be going to 0. And what about the limit of 1/2? 1/2. Limit of a constant is a constant. So this will all end up being 1 divided by 2 times the natural log of 2. That will be this unbounded area. So that's finding all this area in here. All right, any questions on your first improper integration problems? So in our mind, this is exponential decay. Exponential decay is fast enough. This curve is going to approach the x-axis fast enough to get a finite area. So if something's decaying at an exponential rate, it's going to decay so fast that that area is going to be finite. Let's see, let's go ahead. Let's take our break now before we start this one, this left tail problem. I'll leave this one here so you can look at that again if you need to. Let's take a 10-minute break. And if you have questions on right. So in this book, if it's a left tail, they always do A. They think of the interval as A to B. So if it's the left tail, they'll say A goes to negative infinity, B goes to positive infinity. But it doesn't matter. So 0 to negative infinity. So our interval is right here. And the idea is that we're going to create a definite integral by integrating from 0 over to A, or maybe I should say A over to 0. So that is our definite integral is right here. But then we just let A go to negative infinity to see if that unbounded region is finite. Now, just looking at the Desmos graph, it feels like this graph is approaching the x-axis very slowly. It looks completely different than that exponential one that was zipping right down to it. Right? This gap looks like it's closing very slowly versus this gap up here, which is closing very quickly. Not that that's, obviously you can look at a graph and get the wrong idea, but that gives you an intuition that it probably diverges. So if the area is infinite, we'll say that the integral diverges. If the area is finite, we'll say the integral converges. So first step, we're going to turn this into the limit of a definite integral. So we're going to let A go to negative infinity, A to 0. And once again, we're just going to pop this up into the numerator. Whenever we have a power in the denominator, we pull it up top to integrate. And that is done with the power rule. So we're going to have 2 minus x raised to the, when we add 1, we get positive 2/3. Dividing by 2/3 means multiply by 3/2. So that is the power rule part. Add 1, divide. But then what else do we have to do? RCR. The derivative of the inside here is -1. So we also have to divide by -1. So put that negative out in front. So that negative right there, that's our RCR. That's the reverse chain rule from this negative. The derivative of 2 minus x is -1. And let's put our evaluation bar. So that goes from A to 0. So that's where we're at. So add 1 to the exponent, divide by the new exponent, and then divide by the derivative of the base. The base is 2 minus x. Its derivative is -1. So once again, I'll pull this constant out. We know that that constants can move right through limits. So let's just get it out of the way. It's easier to evaluate the limit when you have it kind of uncluttered. So now we plug in our upper limit, which is 0. 2 minus 0 is 2, so we're going to end up with 2 to the 2/3 power minus, plug in a, and we're going to have 2 minus a to the 2/3 power. Two to the 2/3 is a constant. Limit of a constant is itself. No biggie. But we have to look at this thing. So this limit is as a goes to negative infinity. So focus right here. 2 minus infinity is 2 plus infinity, which is infinity. So this part right here is going to infinity. That part is going to infinity right there. Everyone agree? So that 2 minus a is going to infinity.
Aren't we going to negative infinity?
But 2 minus infinity.
Oh.
So a is going to minus infinity, but 2 minus a would be going to positive infinity. And then positive infinity, so as we go to positive infinity, if we look at x to the 2/3, what kind of function is x to the 2/3? What happens in quadrant 1 for any fractional exponent of x? Birdwing? So if we have something like square root of x or x to any fractional exponent, if we just ignore to the right, just over here, that's supposed to be a 2/3 power. So, right, any fractional exponent on x, we get that birdwing in quadrant 1. So as x goes to infinity, this goes to infinity, right? This thing is growing. It's growing very slowly, but it's growing. It's not going to 0. Right? So as we start moving out this direction, this function is going up towards infinity. There's no horizontal asymptote on square root of x or whatever, 3rd root of x or 2/3, doesn't matter. So this function right here, if you think of this as x to the 2/3, this function right here, so now we're going to grab the whole thing, that is going to go to infinity. So this function down here, this is what we're analyzing, x to the 2/3. As we go out towards infinity this way, the y values go towards infinity up. So that limit is going to end up being a constant minus infinity. So constant minus infinity, that's negative infinity. Negative infinity multiplied by -3/2 will be positive infinity. And so what we say is, therefore, we have divergence, or diverges. So an integral diverges if it's not finite. It converges if it's finite. And we use the little triangle of dots means therefore. Okay, any part of that limit evaluation that you're not sure about? And this thing here, this part here, that's just a constant. So don't get tangled up by that. That's just a constant. And a constant minus infinity, 5 minus infinity, that's negative infinity. So constant minus infinity is negative infinity. Negative times negative is positive. Okay. Next one. So we'll do one with the bell curve. It's really two problems in one because we have to break it apart. Doesn't matter where you break it apart. The natural place to break it apart, of course, is 0. So we're going to break it apart right there. So we are going to turn this into the integral. So I'm going to make it the limit as a goes to negative infinity of a to 0. This same integrand plus the limit as b goes to positive infinity same integrand. So that's our breakup. So we're thinking about a over here, so we're going a to 0, and then we're also going 0 to b. So we're treating these as two separate intervals. So a to 0, that's a definite integral. 0 to b, that's a definite integral. And then we take the limits. Okay, so let's focus on the integrand for a minute. And maybe it's even helpful to just pull that whole integral out and just evaluate it like it's an indefinite integral. And then go back in, because we have a lot of limits of integration and things. So let's just come down here and focus on the integral part. So we have x squared plus 2x plus 5, if I remember correctly. So let's just focus on that for a minute. What is our strategy when we have a non-factorable quadratic in the denominator?
Just make it a perfect square.
Yep, make it a perfect square, complete the square.
Oh, yeah, 1 or, yeah.
Yep, so we need a 1 with this integral, with this first part. So x squared plus 2x plus 1 plus 4. Bless you. Divide by 2 and square. So 2 divided by 2 is 1, 1 squared is 1. So we are going to rewrite this as that. And then we see, oh, sum of squares. So we're going to factor out that 4 in the denominator so that we have a sum of squares with a 1. And when we factor out that 4, the leading term has to be modified. So we'll end up with that. All right, if you need to put the 4 over 4 here, of course, that's totally fine. So that the 4 that's being factored out is that one. And then we want to rewrite the x plus 1 squared over 4 as a single quantity squared. And what is that?
Inverse tangent.
Inverse tangent. That is inverse tangent. So this is going to be 1/4. I'm going to leave a little space for RCR. Inverse tangent x plus 1 over 2. This is an indefinite integral, so I'll put a plus c here. We're just sort of doing this work on the side. And what goes in our little RCR gap? 2. Because the derivative in here, the derivative of x plus 1 over 2, that derivative is 1/2. The derivative is 1/2, so we divide by 1/2, which means multiply by 2. So if you want to, so looking at this over here, the derivative of that quantity is 1/2. So dividing by 1/2 means multiplying by 2. So let's just simplify this. This is going to be 1/2 inverse tangent of x plus 1 over 2 plus c. Okay. Let's go back up then. So half arctan x plus 1 over 2. So what we have here then is limit as a goes to negative infinity. And we just integrated and got 1/2 arctan of x plus 1 over 2. And that's going to go from a to 0. And then plus the limit as b goes to infinity. Same antiderivative, 1/2 arctan x plus 1 over 2. But this is going to go 0 to b. All right, any snags up to that moment? Okay with that? So now we're going to plug in our limits of integration, plug in the upper limit. So here, and we can pull half out in front if we want. I'm not going to do it right here because there's none of space really. So plugging in 0, we'll have 1/2 arctangent of 1/2 when we plug in 0. Minus antiderivative evaluated at a. So we have that. So when we evaluated a, all we do is replace the x with an a. And this limit will be as a goes to negative infinity. All right, then we'll do this one. So plus the limit as b goes to infinity. Over here, we're going to have 1/2 arctangent of b plus 1 over 2 minus 1/2 arctangent of 1/2. Okay. So, now we have to take the limit of the variable parts here, the a's and the b's. The other parts are constant. So the constant limit of a constant is itself. So we have to look in here. And let's make sure it's clear what's happening. So inside the arctangent here, a is going to negative infinity. If you add 1 and divide by 2, this inside bit is still going to negative infinity. And so the question is, what does inverse tangent approach as the inside approaches negative infinity? So we have the picture right here. As the inside of arctangent goes towards negative infinity, what does the function approach? Negative pi over 2. So this is going to become 1/2 arctangent of 1/2. That's just a constant. Limit of a constant is itself. Minus 1/2. And we said that this whole piece here, that's all going to approach negative pi divided by 2. And now let's analyze the other one. So over here, same idea. As b goes to infinity, the inside of this is going to go towards positive infinity. So then we look at our graph and we say, okay, as the inside of arctan goes towards positive infinity, the function values go to pi over 2. So this part right here is going to pi over 2. So we'll end up with 1/2 multiplied by pi over 2 minus 1/2 inverse tangent of 1/2. These two cancel each other out. These two are opposites of each other. Opposites cancel. So we're left with pi over 4 plus pi over 4, which is pi over 2. That'll be our cumulative area. A lot of little details in that one. Lots of little details. Any questions on that limit process? So arctangent is going to come up a lot because it's got these horizontal asymptotes, so it can create a lot of finite areas when you're dealing with improper integration.
Do we ever run into problems with having it be the limit or having it go from 0 to b? Because I know in a previous problem we said because it's 0 if we were dividing, it didn't work.
I mean, it's possible that if you got division by 0, it'd be undefined.
So, but, it would
But we shouldn't see it. We should not see division by 0. It might be, what we can see frequently is division by something that's approaching 0, which could go to infinity. Like if you have the limit of 1 over x and x is going to 0, then 1 over a number getting closer to 0 is going to go towards infinity. So we'll see that part. Okay, let's look at this little bump. Again, just looking at the graph, it feels like, ooh, looks like it probably converges. Now, I want to bring your attention back to the very first example we did. The very first example was 1 over x squared, right tail. The very first example, 1 over x squared, right tail, and that was finite. Remember, the area was 1. When we look at the nature of this integral, the numerator, if you go way the heck out into the tail, isn't the numerator just about pi over 2? Right? Arctangent, if you go way, way out, arctangent, it's about pi over 2, which is a constant. So the numerator really isn't doing much. It's just acting like a constant. So this is probably going to behave exactly like 1 over x squared behaved, because the numerator is just a constant. If we have the numerator being constant and the denominator is going to infinity, we still have something that's going to 0 pretty quickly. So just as a backdrop, keep that in mind, that we know that this is out in the tail. It's basically a constant. So first off, we know that this is improper because we see the infinity jumping right out at us. So we're going to take turn it into a limit of a definite integral. One plus x squared plus 1, whatever. So what technique of integration are we going to use here? U sub. Yeah. Because we see that if we let u, the only choice for u is arctan. And its derivative is 1 over 1 plus x squared, which we see. Anytime u sub is going to work, its derivative has to be present. And the derivative of arctan is 1 over 1 plus x squared. Well, 1 over 1 plus x squared is present. If you were to let u equal 1 plus x squared, the derivative is 2x. And there's no 2x's in there. That's an arctan. Right? So there's two choices for the substitution, the numerator or the denominator. You're letting u be the denominator does nothing, because the derivative of x squared is 2x and there's no 2x. But the derivative of arctan is there. So this is actually going to work out way easier than you might suspect. If we let u be arctangent, then du will be 1 over 1 plus x squared dx. And this all turns into a u du. So this will be limit. Arctangent is u. Dx over 1 plus x squared is du. So we have that. And let's go back, let's just put stars here. Doesn't look like fun to convert here, so let's, I mean we can convert, it doesn't matter, but it's going to be easier not to. It'll be easier to go back to the original limits. Because this limit right here is b goes to infinity, yeah, so let's just go back to the originals before we evaluate. So we have that. And then we put our arctangent back in. So we're going to have the limit as b goes to infinity of arctan squared divided by 2. And this is from 1 to b. All right, any questions up to that point? Plug in the upper limit. So we're going to have limit of arctan b squared over 2. We could have pulled that 2 all the way out. That might have been nicer. Arctangent of 1. What is arctan of 1? Pi over 4. We've seen that a bunch. So we get pi divided by 4, quantity squared divided by 2. And this whole limit is as b goes to infinity. And over here we have constant. Limit of a constant is itself. In here, limit of arctan b. As b goes to infinity, that goes to pi over 2. Love it. So this is going to be pi over 2 quantity squared over 2. This is going to be, let's see, we can multiply that out now. So that's going to be pi squared over 32. So we'll have pi squared divided by, that's a 4. 4 in the denominator makes an 8. Multiply this one by 4 over 4. So we'll have 3 pi squared over 32. What do we think? Feels crazy that we're finding areas of unbounded regions. Bless you. Seems like we're starting to do real math. All right. Unbounded regions. Whoever thought? Somebody that didn't have TV. All right. Gabriel's horn. Why are you shaking your head? So Gabriel's horn, this is an interesting paradox. So Gabriel's horn is typically thought of as this region that you get when you rotate 1 over x around the x-axis. So we're going to rotate 1 over x. We've rotated all sorts of curves around the x-axis and found volume. Let's do this one. So 1 over x around the x-axis. So we are going to find the volume of Gabriel's horn. And it's an infinite horn. So this is going to be the integral from 0 to infinity. Excuse me, 1 to infinity. We're going to start at 1. And if we're going to find the volume of the horn, we're going to use the disk method. We imagine a vertical element right there at x. The radius of the disk is right there. So we're imagining, this disk. I don't want to draw it, it'll get messy. You can see the disk. So pi r squared. So area is pi r squared, area of a disk, pi r squared. r in this case is x, 1 over x. So we're going to get pi over x squared. So the volume is going to be the integral of pi over x squared dx. And once again, we've already integrated 1 over x squared twice, essentially. We know that's going to be finite. Oh, and actually I started to do it right down here. So it's that. That's where we're at. So we're going to turn it into a limit, and I'm going to factor the pi all the way out to the front. It's just easier. Get rid of the constants if you remember. And then we're going to integrate x to the negative 2. Integrating x to the negative 2 is negative 1 over x. We've done that one quite a few times. Maybe I'll write, let's make sure that that's clear. So integral x to the negative 2 dx from 1 to b. So we do our integration, and then we'll take the limit. So it's going to be minus 1 over x. As b goes to infinity, 1 to b. So we have minus 1 over b, minus minus 1 is plus 1. And 1 over b as b goes to infinity, goes to 0. So this tells us that the the volume of Gabriel's horn is pi cubic units. Pi cubic units. Okay, so we just showed this. We just showed that the volume is pi. Now, the paradox with Gabriel's horn is this. So it's got finite volume. And down here, we are going to show that the surface area is infinite. We're not going to go through all the details here, but let's just talk about this. So surface area, we know we have to do the 2 pi r times the square root of 1 plus the derivative squared. Exam 1, surface area formula. So 2 pi r, the function is 1 over x, so 2 pi 1 over x, and then the square root of 1 plus the derivative squared. That's what that all says. So don't bother, you don't have to write this down. So this is the surface area integral that we would have got from exam 1, right there. Okay? We can turn this improper integral into the limit of a definite integral from 1 to b. And we have this. Do you agree that this quantity right here, what do you think about that quantity? Look at this integral right here. So the only thing we're going to do is just ditch this integral. We're going to ditch this. And we say that that's bigger than that. Do you agree that this right here, that piece has got to be bigger than 1? Right? If x is a positive number, it's going from 1 to infinity, then 1 over x to the 4th is a positive number, bigger than 1. So this whole thing is definitely bigger than 1, no matter what. Everyone agree? Bigger than 1. So that means if that's bigger than 1 and we take it away, that means that this integral here has to be bigger than this. If we take something away that's bigger than 1, what's remaining, this whole thing has to be bigger than this. Do we agree? So let's suppose we have this integral and we multiply by something bigger than 1. Then it's bigger. If you start with 5 and you multiply it by something bigger than 1, say 2, then you have 10. Right? So if we have this thing and we multiply it by something bigger than 1, this is bigger. Right? So that we can integrate really easily. So let's look at that. So that's bigger than 1. So now let's integrate this piece right here. So let's focus down here. The 2 pi is obviously constant. The 2 pi is constant. So let's just focus on the integral of 1 over x from 1 to infinity. So this limit right here is going to be limit as b goes to infinity. What's the integral of 1 over x? Natural log of x. So we have natural log of x, absolute value of x, but x is going to be from 1 to b, so it doesn't matter. It's positive. So then we have limit of natural log of b minus natural log of 1. And natural log of 1 is 0. So we have limit of natural log of b as b goes to infinity. And what is that limit? Natural log function is growing. So if we look at a picture of the natural log function, it looks like this. Doesn't it go to infinity? So as we go this way, the y values go to infinity. So this limit is infinite. So therefore diverge. So this is what we've just decided. We've got this infinite horn. It's got finite volume, but it's got infinite surface area. This is one of the first weird shapes you get that has some of these things you have to think really carefully about. So finite volume, but infinite surface area. So the way they state Gabriel's paradox is that if it has finite volume, you can fill it with paint. But if it has infinite surface area, it can't be painted. But if you filled it with paint, it's painted. So how do you resolve that paradox? So everyone followed? So if it's got finite volume, you can fill it with paint. Take a can of paint. If it's finite volume, what do we find? How much paint do we need? Pi cubic units of paint. Fill it with paint. But if it's got infinite surface area, you can't paint an infinite surface. But if you just filled the whole darn thing with paint, then the inside is painted, and since it's paper thin, it's painted. So how do you resolve that paradox? We'll talk about that next time. So think about that. Think about that. But it's an interesting mind game. And this, when you get to this level in calculus, there's going to be a lot of these things. And you all know probably of curves that have are finite in length but nowhere differentiable. Did you talk about that in Calc 1? Like you can make these weird curves that are, like we're going to look at one called the Koch snowflake. The Koch snowflake's going to have infinite perimeter but finite area. So you're going to be able to create these weird shapes by having curves that sort of have lots of little variation on the boundary. So we'll do the Koch snowflake once we get into chapter 10. So this is just one of those examples. You can come up with solid objects that have finite volume but infinite surface area, just like this. There's all sorts of them. And this is kind of an interesting first look at one of those types of things. Okay, let's do something less thinking oriented. So the region bounded by this and the x-axis on the interval is rotated around the x-axis. So we're going to take that, we're going to rotate it around the x-axis, and we want to find the volume of that. Now when we look again at the graph, I like putting the graph in just as kind of a guidepost. It looks like this curve is not approaching the x-axis very fast. Right, so we are going to suspect. Our suspicion is that it probably is not going to be finite, because it doesn't look like it goes to the x-axis fast enough. Again, it's just a graph, though. Graphs are deceiving. But that would be our hunch just looking at that graph. Okay, so it's rotated around the x-axis, so we're using disks again. So there's your radius. The disk is however you want to draw your disk. You know, it's like that direction. The area of a disk is pi r squared. That's something that has not changed. So the area of the disk in this particular case is pi times that function squared. So we're going to square the function that we're given. That'll be the area of the disk at x. All right, so volume will be the integral from 0 to infinity, because this curve goes on forever. So 0 to infinity of pi r squared, the pi can come to the front. Squaring the numerator gives x. Squaring the denominator gives x squared plus 1 to the 2/3. So that will be our volume integral. It is improper, this integral. So we immediately turn it to a limit of a definite. And this limit will be as b goes to infinity. So we're going to go 0 to b. And we're going to turn it into a definite integral and then take the limit of that. All right, so that's what we always do. Every time we see an improper integral, turn it to a limit of a definite. And let me just say one thing about this. Hopefully, when you look at that, what you should be seeing is that that is a function of b. That green box, this is a function of b. Let's just go back for a second and look at any of these. So when we get down to the end, right, we have a function of b that we take the limit of. So this integral right here, as soon as we get a b, this is a function of b. And then in the very end, we take the limit as b goes to infinity. So this is a definite integral, but it's different than a definite integral where you have numeric limits of integration. With a definite integral, if you have numeric limits of integration, you always end up with a constant at the end. But if you have a variable in one of the limits of integration, you end up with a function. And then we take the limit of that function. So when you're looking at that, that's what we're doing. We're finding a function that's measuring partial volume, and then we're taking the limit as b goes to infinity to get total volume. In this case, volume. What integration technique is going to work beautifully here? U sub. Right? Because if we look at x squared plus 1, its derivative is 2x. That has to be somewhere if it's going to be useful, and it is. In the numerator, it's not exactly 2x, but it's close. So we're going to let u be x squared plus 1. du will be 2x dx. And if we divide both sides of this equation by 2, we'll have an expression for x dx. So we will have pi multiplied by limit. And then in here, we're going to convert to u's. We're going to go back to x's in the end, so let's just put some sort of placeholders. U in the denominator, that's going to be u to the minus 2/3. If we pop it up to the numerator. And then x dx is du over 2. So we're going to put the du right there, and the over 2 is out in front. Dividing by a constant, pull it to the front. Easy integral, power rule. So we will have u to the 1/3. Divide by 1/3 means multiply by 3. And again, we're just using placeholder limits for a moment. That 3 can come to the front now, so we have 3 pi divided by 2 out in front, multiplied by limit. Plug back in our u. So x squared plus 1 to the 1/3 power. And now we're back to our original limits, which were 0 to b. Plug in the limits. So we'll have 3 pi over 2 multiplied by limit as b goes to infinity. Here's where we will analyze the limit. So we're going to have b squared plus 1 to the 1/3 minus 1. One to the 1/3 is just 1. And this limit is, so b squared plus 1, b squared plus 1 is going to infinity. And so once again, we have a bird wing. So in here, this is going to infinity, inside there. And a 1/3 power, that's the bird wing stuff. We have this function right there. As we go right, we're going up towards infinity. So that whole quantity right there is going to infinity. Subtracting 1, of course, doesn't change that fact. Multiplying by 3 pi over 2 doesn't change that fact. So we end up with plus infinity, so therefore we have a divergent integral. So as we suspected by looking at the graph, those cross sections weren't coming down tight enough to the x-axis. So we have infinite volume. So this whole improper integration thing, it's a process for sure. Not quite as procedural as, say, PFD, but it is definitely on the procedure side. So you have to remember the steps. Take your improper integral, turn it into a limit of a definite integral, evaluate your definite integral and get a function of b, and then take the limit. That's the process. Let's do vertical tails. So vertical tails act very similar to horizontal tails. The thing that is that's very subtle is that you don't look at an improper integral that has a vertical tail in C infinity. With the horizontal tails, you just look into the limits and you say, oh, infinity or minus infinity, it's improper. Now I know I have to take the limit of a definite. Right? You look at this, you can't tell. You cannot tell just by looking at the function, by looking at the limits of integration on the function. You can't tell. So here's the concept. So we are going to integrate from, here's our interval, a to b, but the function is undefined at a. So we get this vertical tail. So what we're going to do is create same type of thing. We're going to create a definite integral from c to b, and we're going to let c approach a. It's going to approach a from the right of a, if the vertical asymptote's on the left side. If the vertical asymptote's on the right side, same idea. There's our definite integral. And then we're going to let c approach b from the left side. So really important here is that we are dealing with one-sided limits. So there are one-sided limits here. So that's an important thing. If we have two sides, you do what you probably think. You integrate on the left, you integrate on the right, and you add them together. In order for that whole volcano-looking thing to be finite, both sides have to be finite. So we have to integrate twice. We have to do the left side and the right side, and that has to add. Both those have to be finite to have a total finite area. Okay, so these are vertically unbounded. Let's try one. So here's our first function. We're going to look at 1 over x squared again. This one we already did. We know that this is 1, right? We already integrated that. We know that that area is 1. But what about the vertical tail? Let's look at the picture. So when you look at the horizontal tail, that's this one. That's that one. That's finite. You can tell that the curve is pinching to the x-axis super fast. But when you look at the vertical tail, so when we integrate from 0 to 1 here, this area, you can tell that the vertical tail is not grabbing the y-axis. It's not converging to the y-axis nearly as fast. And we are going to see with these curves that we have kind of a whack-a-mole thing. If this tail gets to the x-axis really fast, it's going to be pulling this tail away from the y-axis. And vice versa. If it starts peeling off the x-axis, it's going to come into the y-axis faster. It can't do both. We are not going to be able to have a smooth function that is tight on x and tight on y. It's going to be one or the other. So here, we already know it's tight on x. It's not going to be tight on y. So we expect this to be infinite here. So let's check. But now when you look at it, you look at that, it doesn't jump out at you that that's an improper integral. Right? You don't see infinity anywhere. But what you were told in Calc 1, but didn't really pay attention to, is that for this to be a definite integral, your function needs to be continuous on the interval. Is 1 over x squared continuous on 0 to 1? No, it's not defined at 0, so it's not continuous at 0. So that's how you will recognize that it's improper, that one of the endpoints gives you an asymptote, gives you a vertical asymptote. So it's not going to jump right out at you, but if you look at your integrand, you will see that you have an asymptote. All right, so this is, once again, it immediately turns into the limit of a definite integral. So we're going to do this. And now c is going to go to 0 from what side? The right. So the interval is 0 to 1. So right here is 0 to 1. There's 1 right there. And we're creating a definite integral. So here's our definite integral. And there's our c value. And c is going to 0 from the right side of 0. Right? It's coming in through positive values to get to 0. It's coming from the right. So that c is going to approach 0 from the right. And then we do what we've done already today. We integrate that function, add 1 to the exponent, divide by the new exponent. Once again, we get negative 1 over x. This will go from c to 1. So we'll have minus 1c, 1 over c, plus 1. As c goes to 0 from the right. Super important that that's one-sided. So now we take the limit. The limit of the constant is itself, but we have to focus here. We are not taking the limit as c goes to infinity. Right, we're taking the limit as c goes to 0. Moreover, c goes to 0 from the right. So we start thinking about values of c. Think about plugging in 1. Think about plugging in 1/10. Think about plugging in 1/100th. So we want to approach 0 from the right-hand side. So positive values. 1, 1/10th, 100th, 1,000th, 1/10,000th, etc. What is happening to this fraction as c goes to 0 from the right? What is that approaching? What kind of infinity?
Negative.
Negative infinity. And if we add 1 to it, it's still going to approach negative infinity. But I'm not happy. Hold on one second. Why am I not happy? Because that area there looks like it should be positive infinity, not negative infinity.
I think you may have forgotten the minus sign.
I feel like I must have somewhere.
Did you flip your sides? Because you have C on the left, not on the right. When you
Oh, that's what I did. Right? The left side, it should be c. Oh, no, c to 1. Did I switch them? Oh, I see where I did it. Yeah, right here. these are reversed, right? It's the upper limit first, right? We do upper limit minus lower limit. So the upper limit is 1. Upper limit is 1. So this should be -1. Minus a minus is plus 1 over c. There we go. That's better. Everyone agree with that? So then this part here, like you just said, this part here is as we approach 0 from the right, this part is going to go to positive infinity because there's no minus in front of it anymore. So then positive infinity minus 1 is still positive infinity. So therefore diverge. So we have a divergent vertical tail. So this is a pattern we are going to see again and again. If we have a convergent horizontal tail, we're going to have a divergent vertical tail. If we have a convergent vertical tail, we're going to have a divergent horizontal tail. That's going to be a pattern that we are going to see repeatedly. So here's kind of the opposite case. So we've seen that when the power of x gets bigger and bigger in the denominator, so x to the 2, x to the 3, we have a convergent horizontal tail. Now let's do the opposite. Let's let the power of x get tinier. When the power of x gets tinier, less than 1, we're going to see that it's going to get super tight on the y-axis and peel off of the x-axis. So we're going to have the opposite scenario. So let's look at the vertical tail first and show that that's going to be finite. So coming here, we're going to immediately convert it over to a limit as c goes to 0 from the right-hand side. And this is going to be an x to the -1/4. And we are going to 1, which is right here. So we're picking the c value right there. So we're integrating from c to 1. And then c is going to creep over towards the y-axis. All right, so integration here, power rule. X to the 3/4 divide by 3/4. So we get that. And then we're going to plug in the limits. We can pull the 4/3 to the front. So we're going to have 1 to the 3/4, which is 1, minus c to the 3/4. As c goes to 0 from the right. And what is that limit as c goes to 0? So the total value will be 4/3. Because what does c, what happens here? Where does that go as c goes to 0? 0. Right? 0 to any non-negative power is 0. So we have 1 times 4/3, which is 4/3. So that means that we have a convergent vertical tail, which is, looking at the graph, that makes perfect sense. So convergent vertical tail. And let's show that the horizontal tail does not converge. So let's go horizontal now. So we're going to integrate from 1 to infinity, x to the -1/4. So that's the horizontal tail. We see the infinity, so here it's more obvious. We're going to let b go to infinity. And this will be the integral 1 to b, x to the -1/4. So then we do the same thing we did up there, add 1 to the exponent, divide by the new exponent, so we get the same exact antiderivative. Plug in our limits of integration, factor out the 4/3. we're going to b to the 3/4 minus 1 as b goes to infinity.
Yeah.
I don't know what special relativity.
And what does b to the 3/4 do as b goes to infinity? Goes to infinity. It's the bird wing. Goes up. It goes up, up, up. Perhaps slowly. As we go to the right, it goes up. So y equals x to the 3/4. So any fractional power on x, we have that bird wing thing happening in quadrant 1. So this part is going to go to infinity. That means that the whole thing is going to infinity. Therefore, we have a divergent area. Diverge. So therefore, it diverges horizontally but converges vertically. And so that is our pattern. Power of x in the denominator. The power is greater than 1, we are going to see that it converges horizontally and diverges vertically. If the power is less than 1, we're going to see the opposite. Less than 1, converge this way, diverge that way. All right, so let's do one example where we have an asymptote that's a little bit obscure. This one's over at -3. So I've highlighted the interval that we're looking at, -3 over to +1. So the thing that is really important is that you've got to just, and actually I will tell you on the exam, but it is important, you need to be able to realize that this is an improper integral when you look at it. And so the habit that you want to get into is looking at your limits of integration, plugging them in, and you notice that this is a bad endpoint. You notice that if you plug in -3, you have division by 0, which means you have a vertical asymptote at -3. So that tells us that it's improper, because this function is not continuous on -3 to 1. Okay, so here, let's look at our interval. So we're going to call this C. We're going to call that 1. So we're going to integrate from from C to 1. So we're going to find this area. That's a definite integral. And we're going to find this area as a function of C. And then we are going to let C approach -3 from which side? From the right-hand side. So this, immediately we jump to limit. So C is going to approach -3 from the right. Integral from C to 1. And let's just pull this up into the numerator. So we know that when we have a power in the denominator, we just pull it into the numerator and integrate. Now, before we actually evaluate this integral, think to yourself, with improper integration, 90% of the time, the math should be confirming what you think. 90% of the time, it should be doing that. So let's think, what are we thinking is going to happen here? So we have a vertical tail, and is the power on x less than 1 or greater than 1? Less than 1. 2/3 is less than 1. So our hunch is that this will converge vertically. Because the power is less than 1. Less than 1 means that we have vertical convergence and horizontal divergence. If we went from 0 to infinity, we would get divergence. So our hunch, this should be convergent, because we have a power less than 1 and we're looking at a vertical tail. Okay, so let's, Jesus, question?
Shouldn't it be -2/3?
It should be, thank you. -2/3. All right, so let's go through the power rule and reverse chain rule here. So we add 1 to the exponent. That gives us positive 1/3. Dividing by positive 1/3 means multiplying by 3. So that's the power rule part. And then what's the RCR part? Divide by 2. So we look at the inside. Its derivative is 2. So the derivative of that is 2. We're integrating, so we have to divide by that derivative. If we were differentiating, we would multiply by it. So then this is c to 1. Pull the 3/2 out to the front. Plug in the upper limit. Upper limit first. 1 times 2 is 2. 2 plus 6 is 8. 8 to the 1/3 is 2. So we have that. And this limit is as c goes to -3 from the right. And what does 2c plus 6 approach as c approaches -3? 0. And so remember that the first thing we always do with an evaluation of a limit is plug in the number. And if you get a value, you're done, because it means that that function is continuous at that number. In a continuous function, the limit and the value are the same. So if you plug in this number right there and you get a constant, then you're done. You don't have to do any weird manipulation. If you plug it in and you get an indeterminate form, then you have to do something. Here we plug in -3, -6 plus 6 is 0. So that tells us that this part goes to 0, which tells us that we end up with a limit of 2, and we end up with a final area of 3. So we're finding, we're doing the vertical tail here, so we're finding all that area right there. So that area is all equal to 3. All right, questions on any of the setup there? Or on the evaluation? So if you look at, let's just jump to this last slide for a minute. So look at this slide carefully, because what we have discovered today is the threshold for convergence and divergence in different scenarios. So let's just look at this graph for a minute here. So y-axis, x-axis. The black curve is 1 over x. The black curve, 1 over x, diverges in both places. 1 over x diverges in both places. But as soon as you start pushing down and getting closer to the x-axis faster, it pulls off the y-axis when you have a power of x. So the red curve here, I bumped up the power of x just to 1.1. If that exponent is just a smidge over 1, that's enough to create this scenario where it gets tight enough to x and it's pulling off a y. So if you bump it up just a little bit, that's going to converge horizontally and diverge vertically. If you bump it down a little bit, that's the blue curve, bump it down a little bit, it's going to pull it off x so that you have horizontal divergence, and it's going to tighten it up on y, and you're going to have vertical convergence. So this is a really good slide to play with, just to make sure. You can do it in Desmos, graph it a few times. But you're going to have the whack-a-mole thing. If it gets tighter to x, it's going to pull off a y. If it gets tighter to y, it's going to pull off of x. And the threshold is a power of 1. Bigger than 1, converge, diverge. Smaller than 1, diverge, converge. It's just going to flip-flop. And yes, you will see the improper integral lots of times in the future. The coolest is when you get to something called a Laplace transform. That is what a Laplace transform looks like. If you're going into engineering, you will see lots of Laplace transforms. And they're super cool because you can take, if you have a function, a lot of times you're studying electricity that's alternating, and the graph of it's going to be a discontinuous function. It's going to have points of, shouldn't say discontinuous, I should say non-differentiable. So you get these curves that are like square curves, and you can't integrate them because you've got these vertical spots on them. If you apply a Laplace transform, you can then analyze non-differentiable functions, which is kind of interesting. We'll talk about more later. Because we're going to do differential equations next week. Yeah. All right. It's not going to snow on Wednesday this week. Oh wait, it's only Tuesday, right? I'll see you on Thursday. Yeah, we'll do some differential equations Thursday. It's not going to snow on Wednesday this week. So make sure you come to campus tomorrow. Originally, they were predicting snow again on Wednesday.